Welcome back, class. Today we're going to discuss the topic of polynomials and or exponential systems. Over the last 6-7 weeks, we have really talked about how equations that were given in algebra are these things that are more or less used to model physical systems that exist in the world around ourselves, whether we're talking about physical systems in astronomy or whether we're talking about physical systems in finance or somewhere else, maybe welding, machining, these kinds of things, engineering in general. These are all going to be ways that we can perform calculations in order to understand the physical world around ourselves or the behavior of things within the physical world around ourselves. And what's interesting is we've discovered that equations largely obey the rules of algebra. It's assumed that every single equation that we're dealing with in this class is going to have real numbers. And because real numbers obey the rules of algebra, the equations themselves, even ones with a bunch of variables, because the variables themselves are just real numbers, will also obey the rules of algebra that real numbers obey. So all of our equations are going to obey the commutative law. They're all going to obey the associative law. They're all going to obey the inverse and identity and or distribution laws. And of course, there are a lot of nuances to the specific ways in which these laws are used, but over the last 6 weeks or so, we have been working to understand all of the different methods by which you can perform, say, equation balancing from one side to the other side of an equal sign. And so, what we saw last week, and actually over the last 2 weeks, was that the solutions to equations may also not necessarily be determined algebraically, but in addition to determining the solutions algebraically, we may also determine those solutions geometrically. So what this means is we're able to open up an entire new dimension to analyze for analysis, so that we can analyze these physical systems. If we can describe the physical system in terms of geometry, we know that we can find a solution to that physical system. But more importantly, if we can describe the physical system in terms of algebra, which is nice to us because we're used to algebra, we know that we can then take that algebraic expression or equation and then plot the behavior on what is known as a Cartesian plane. And from the graph itself, we may also be able to determine geometrically what the solution happens to be. So whether you're approaching a problem from geometry first in order to find the solution, or whether we're approaching the problem using algebra, and then from the algebra, we can plot the geometry and then find the solution. Either way, the destination is the same. And over the past couple of weeks, we have, of course, studied what are known as linear equations in quite a bit of detail. And so for this particular section, chapter 5, what we're going to do is we're going to study what are known as nonlinear equations. It turns out that the vast majority of equations that model the physical world are not necessarily linear. And specifically, we're going to talk about nonlinear polynomial expressions. And with polynomial expressions, we're going to learn how to add, subtract, multiply, and divide polynomials. All right, so buckle up, everybody. Let's dive right in. And so in chapter 5.1, what we are discussing is this idea that as mathematicians were studying these different physical phenomena, whether it be the motion of bullets, i.e., through the air in a parabolic motion style situation, whether we're studying the forces being applied to an object, whether we're discussing any of these different variety of physical situations, we may classify the types of equations that emerge in the mathematics into different families. Now, when we're looking at, say, an equation, a polynomial equation, or any equation for that matter, not necessarily just polynomial, but let's consider the following. Maybe we look at
something such as 7x plus 1, since we were dealing with what were known as linear equations, where we had an expression such as y is equal to 7x plus 1. And if we just analyze this right side of the equal sign, you can just say we have this expression 7x plus 1. And suppose we wanted to discover the difference between the behavior that is produced by a system that is governed by 7x plus 1 as being the equations that determine the physical properties of the system versus the behavior of equations that are modeled by 7x squared plus 1. On the one hand, we might scan through this equation, and you'll note that the coefficients that are in front of my x term are basically the same between the two. And in fact, the number that's being added out in front is also the same. Indeed, the number of terms in our expression is the same. We have, in this instance, 2 terms. And really, the only difference between these two expressions happens to be that the 7x is raised to the first power, whereas the 7x squared would be raised to the second power. Remember that anything raised to the first power is just that something. So even if we didn't necessarily write 7x as 7x to the first, we're supposed to know implicitly that we have an item or an object that is being raised to the first power. And so what we would say about these two different physical systems is that they're only different in terms of the degree of the equation, or the exponent, the highest exponent inside of the equation. We would say that the first equation has a degree of 1, since we have that 7x term raised to the first power, and that's the highest degree that will exist there. Whereas this 7x squared term would be of degree 2. And if we had a third physical system that we might be analyzing, maybe 7x cubed plus 1, we would say that this system's degree would be 3. And, we could keep going from here. 7x to the fourth plus 1, we would say that this system's degree is 4, so on and so forth. So we'll just introduce this property of nonlinear equations called degree. So the definition: the degree of a polynomial or a nonlinear system is simply the highest exponent value of a polynomial expression. That is the degree of the expression. Okay, and we would say that the degree is one thing that we can look at and tell from a polynomial expression right away will indeed determine that the behavior of a specific polynomial expression will be radically different. Now, the reason why I say radically different between, say, that the behavior rather will be radically different between, say, 7x plus 1 and 7x squared plus 1 and 7x cubed plus 1 is that if we were to actually graph these systems, suppose you had a y is equal to 7x plus 1 and you went to give yourself some x points. Of course, we always start with giving ourselves some at least 3 points for our independent variable x, and then we of course calculate the corresponding y value for our dependent variable y. So I'm going to plug in, say, a -1 for my x value, and we would naturally determine what the corresponding y value happened to be. So 7 times -1, that would be a -7. Of course, when we add 1, we would get a -6. If I, evaluated my expression at x is equal to 0, we'd have 7 times 0 plus 1, which would give me 0 plus 1. So this is my equation evaluated when x is equal to 0. And my y would be 1. If I evaluated my expression at x is equal to 1, I would get 7 times 1 plus 1, or 7 plus 1, which gives me 8. So to be specific, we have -6, 1, and 8 as the behavior of our system. Now, looking at 7x squared plus 1. When you evaluate this at -1, you're going to get some really different behaviors going on because once you raise the -1 to the second power, -1 times -1 is +1, and 1 times 7 gives you 7. So now we've got 7 plus 1, which gives us 8. So for this second equation, we have our table, but here we get a +8 for the first value, -1. And indeed, if we plugged in 1 into this equation, 7 times 1 squared plus 1 would also give us a +8. If I plugged in a 0 for that equation, 0 squared is 0, 0 times 7 is 0, 0 plus 1 gives me 1. So I would have this specific behavior that emerges. So to be clear, for our first equation, we would have -1, and we'd be all the way down at -6, somewhere down here. At 0, I would be at 1, and at 1, I would be all the way up here somewhere at 8. So you get a straight line as being the geometrical representation of the behavior that emerges from this particular system. But for our second equation, if we were to plot this, we'd get a rather different looking set of behaviors that emerges. In fact, you would see that you actually have a parabolic situation where at -1, you're all the way up at +8. So you've got something like this. At 0, you're at 1. And at +1, you're at 8. So what's actually happening is you would have a parabola that looks kind of like this. And when you look at the equation y is equal to 7x cubed plus 1, even stranger behavior emerges. Because, if you look at, say, -2, -1, 0, 1, 2, and you analyze the corresponding y points, well, at -2, -2 cubed would be 8. 8 times 7 is 56. 56 plus 1 gives you 57. So you'd be all the way up at +57. -1 cubed is -1. -1 times 7 is -7. -7 plus 1 gives you -6. So now 0, 0 cubed is 0. 0 times 7 is 0. 0 plus 1 is 1. 1 cubed will be 1. 1 times 7 is 7. And then 7 plus 1 gives you 8. And then 2 cubed is 8. 8 times 7 is 56. 56 plus 1 gives you +57. And actually, let me go back and let me look at this -2. I don't know if it'll be at +56. -2 cubed, that'll be -2 times -2 times -2. So it should give you -8. -8 times 7 plus 1, that'll be -56 plus 1, which gives us -55. So we should have been at -55. Okay, so what's actually happening here is rather different than everything else we've seen. At -2, we're all the way down at -56. At -1, we're at -6, so somewhere like here. At 0, we're at 1, so we're over here. At 1, we're at 8, so we're like over here somewhere. And at 2, we're all the way at 57. So you've got this equation whose behavior, and again, this isn't a perfect graph, but the behavior of this equation is more or less like this. So it's kind of like this S shape. And so I hope that students can see that as we raise the exponent of a specific expression, the behavior that emerges in our graph changes radically because of nothing more than the exponent itself. Now, not only do we have to worry about the exponent, but it also turns out that the number of terms within a specific expression is equally important. While for linear equations, there's really only two different ways that we could see a linear equation. You might have y equal to some constant like 5, or you could have y equal to, say, x plus 5. Either one of these equations you would consider to be a linear equation, but the number of terms would be naturally different. So y is equal to 5. This would be a linear equation where y is essentially being intersected. There will be just a straight horizontal line at the y-intercept 0, 5. Okay, if you guys remember. Whereas y is equal to x plus 5, this would be an equation where, again, at the y-intercept 0, 5, you would have a line that's passing straight through it, but you would have a line that is going upwards diagonally. So you'd have something that looks kind of like this. Okay, so it does appear to be the case that the number of terms of an expression is also equally important to the specific behavior of that expression. And we see that just from the linear equations themselves. And so not only is degree important, but we'll also say that depending on the number of terms within an expression, we will be able to classify or categorize the behavior of the expression itself. So the number of terms, in this case, when you have two terms, you call something a binomial. So each one of these expressions that we had in our table would all be classified as binomials, because each one of these 7x plus 1 has two terms, 7x squared has two terms, 7x cubed has two terms, 7x to the fourth has two terms. Note, when I say terms, I'm not referring to the amount of numbers in an expression, where here we have, what is it, two actual numbers and x is a variable. What I'm referring to instead is the individual blocks or individual units of a calculation. So you would look at this 7x plus 1 and we would say, look, we would first have to deal with x times 7, whatever that x happens to be. And once we have that, we're going to then add it with 1, which is its own individual thing floating off in space. So we would say that it has two terms because there is this separation between the 7x and the 1 that is punctuated by the addition operator. Okay, but here for 7x squared plus 1, students might say, well, yeah, but there are three different numbers. There's the 7, there's the exponent, and the 1, right? But here again, what we're looking at is we're looking at the number of individual units within an expression. And so the 1 is floating out into space. We're not even dealing with that until we've finished, say, raising x to the second power and then multiplying that with the 7. And once you've done that calculation, then you would then combine the two. And so we would say that there are indeed only two terms here for the 7x squared plus 1. And likewise for the 7x cubed plus 1, there again, we only have two terms. So if you have one term, which would be an example of one term would be like an x squared or an x or just a number itself, or even 7x to the third. This would all be single term expressions, and this would be called a monomial. Note that we use Latin words to describe and or categorize our algebraic expressions depending on the number of terms they have. So mono means one in Latin. Miol is essentially a suffix that tells one that you're dealing with a polynomial expression. So IAL is the suffix for a polynomial, but you might also note that nom means number. So indeed, this is like one number. Because if you knew what your x was, even for this expression 7x cubed, at the end of the day, say your x was 0, then what you're really dealing with here is you've got 0 raised to the third power, which is 0, and 0 times 7 would be 0. So you would just have one number after you've determined what your x was and you performed all of the subsequent addition, or I'm sorry, the subsequent multiplication operations. Okay, if we have two terms, this would look like, maybe an x squared plus x. Maybe this would look like a 7x plus 3. Maybe this would look like 3 plus x cubed plus x to the fifth, so on and so forth. Any type of situation where you have exactly two different terms that are independent from each other that cannot be added according to the like terms rule, this is what we call a binomial. Bi meaning two in Latin, and meal, of course, simply meaning number or polynomial.
Whenever you have an expression that has three terms, it can look like the following: x squared plus x plus 1, 7x squared plus 3x plus 5, 5x cubed plus 3x plus 7, 8x to the fourth plus 2x squared plus x, something like this. Anything like this where we have three different terms that are all
being either added with each other or subtracted from one another, that is going to be what we refer to as a trinomial. Tri meaning three in Latin. And it turns out that trinomials are really important from a math theoretic perspective because trinomials will, in many instances, be what are known as factorable. They'll be factorable expressions. And not only will you be able to factor them, but you usually get some nice solutions out of actually going through the process of factoring them. When you deal with binomials, usually the solutions to polynomial equations are in the form of binomial factors in many instances. Binomials themselves are pretty easy to factor in cases where you don't have what are known as prime polynomials, which we'll talk about here in a minute. And monomial expressions obey interesting rules that are essentially an extension of our ordinary rules of algebra. So whereas you have the commutative, associative, and distribution laws in an algebraic context, it turns out that when you're dealing with exponential expressions, such as an x raised to the third power, and then you start to exponentiate these exponential expressions, the exponential laws are analogous to the ordinary rules of algebra, which is pretty interesting. So at any rate, we tend to categorize all of the different formulas or equations that we encounter in the lower level mathematics as in terms of either their degree, i.e. the highest exponent of the expression, or in terms of the actual number of terms or entities that exist within the expression. So just as a couple of examples, if they asked us to determine the degree of the expression, and maybe they give us something nasty, maybe they give us a p squared q minus 8p to the third q squared and plus 3. And they might ask us, what is the degree of the polynomial? The degree of a polynomial is interesting because it's very analogous to the ordering of the digits of a number. If you have a number like 150, we know that the digit here on the right stands for hundreds. We know that the second digit stands for tens, and the first digit stands for ones. It turns out that the degree, very similarly, is important for determining the polynomial behavior in the same manner that hundreds versus tens is important for being able to perform addition and subtraction on ordinary numbers. And so the first thing that you do whenever you're given a random polynomial expression is you're always going to rewrite that polynomial expression in terms of its highest degree. So in this instance, I see that negative 8p cubed q squared is the term which has the highest exponents. So I'm going to go ahead and put it up in front. And I can do that because the commutative law applies for these individual terms of an expression just as much as it would apply for ordinary numbers. So I can switch the order of 8p cubed q squared without really doubting that I'm doing something that violates the laws of algebra. just by considering what would happen if I plugged numbers into this equation and performed a calculation. We would say then that the degree of the polynomial happens to be 3 because I apologize, not 3, but actually 5. The degree of the polynomial happens to be 5 because you have the first term being raised to the third power and the second term being raised to the second power. So what happens here is you can essentially just add the terms together. So 3 plus 2 gives you 5, and you would say that the highest degree is therefore 5. Similarly, the degree of the second term, as it turns out, it would be 2 plus 1 or 3 because the q almost behaves as a q raised to the first power, whereas the p acts as a p raised to the second power. So when you add those degrees together, you would say it is now for the second term would be a term of degree 3. Okay. Another example, if you had something like 7x cubed plus 3x plus 5, they ask you what is the degree of the polynomial. You would say that this is a polynomial expression of degree 3, since your highest exponent happens to be a term raised to the third power. So that is our highest exponent. So we would say degree 3. If the problem statement asked you whether or not this was a binomial, monomial, or trinomial, you would say that this is indeed a trinomial expression because you have 3 different terms that are all separated by an addition or subtraction operation. Up here, you would similarly, if you were asked the question whether this particular polynomial was a trinomial, binomial, or monomial, you would say that I've got 3 different terms that are all being added with one another. So this is indeed a trinomial expression.
When it comes to um, adding or subtracting polynomials from
One another, it turns out that you may add or subtract polynomials according to the rules of ordinary algebra, so specifically the associative law and a commutative law, where the only thing that we have to watch out for is the degree of the terms being added with one another. So say you have 7x plus 5, and I take this polynomial, in this case, this binomial, and I add it with 8x plus 4 and ask the question, what is this equal to? Well, by the associative law, we know that we can remove our set of parentheses. By the commutative law, I know that I can then group up my x's with x's, my apples with apples, or my numbers with numbers, and I'll have 7x plus 8x plus 5 plus 4. Now, 5 plus 4, we would obviously be able to add together and get 8. The 7x plus 8x, while there are many students that would say, oh, okay, well, I've got 7 bananas here, 8 bananas here, so I should have 15 bananas in total, right? It's useful to remember that the reason that we're able to add these x's with x's is simply because the x's obey the distribution law in reverse. So you may say factor out the x, and you've got 7 plus 8 inside of parentheses, or said another way, you have 15x inside of your parentheses. And so the answer to adding 7x plus 5 with 8x plus 4 is that you would have 15x plus 9. Now, let's go ahead and see if we can add polynomials that are a little bit more complicated, those, because we should have been able to do this coming in from, say, Math 900 or our lower level algebra courses. But suppose that you're given some sort of nasty polynomial expression such as TP squared Q plus 5PQ squared plus PQ, and we're maybe adding it with 3P squared Q plus 9PQ squared minus 6pq. And the question is, well, what do we do? By the associative law, because everything is being added together, you may remove the parentheses. So we can just rewrite this expression in the following manner.
And then, of course, you can group your terms together. But what we're going to do
specifically is we're going to group our p squared q's with p squared q's. And we're going to try to make sure that we don't confuse this with our pq squareds and our PQ terms. Okay, so you've actually got three different types of terms that you're dealing with in this particular expression. You've got P squared Q terms, you've got PQ squared terms, and you've got PQ terms. And those cannot necessarily be added together with each other. So we can add two P squared Q terms with P squared Q terms. So we've got 2P squared cube plus 3P squared cube. We can also add the 5pq squared with the 9pq squared. And finally, we've got the pq minus 6pq term left over.
Okay, so PQ minus 6PQ is going to give me 5PQ. 9P squared plus 5P squared, that's going to be 14PQ squared. And then 2P squared cubed plus 3P squared cubed,
That's going to be 5p squared cubed. So that would be your answer. Now, students would ask, however, how did I know that you can actually add these things together apart from being the teacher? And what I would tell students is go back to the basics of factoring an expression, or said another way, using distribution in reverse. When you've got this 2p squared q term and 3p squared cube term, what you've got is a 2 times p plus 3 times p times a q. And because you see the same terms here and here, by the distribution law, you may write those terms out in front of your sequence of parentheses. So you've got a p squared q on the outside, and 2 plus 3 gives you 5. Now, if you had tried to add this p squared q term with maybe a PQ, here's the problem. Here's the problem that you would encounter. The reason you cannot add these terms together, apart from saying they're not like terms. In fact, the reason we would say they're not like terms is because when you look at the base terms that are included in each of these terms, so like the p squared, for example, is actually p times p. So 2p squared q would be 2 times p times p times p. And 3p squared is 3 times p times q, and this pq is just itself pq. Then I hope you can see that you're not dealing with the same number of p terms, even though the number of q terms happens to be the same. So if you were to factor this, i.e. use distribution in reverse, you've got, I can only take a p out of everything, so I've got 2p and 3p. And while I can take a q out of everything, what would be left over is you would have this 2p plus 3p term, or said another way, 5p plus 1, which was just hanging out and representing the fact that you had a pq here on the back end. And so you've got this 5p plus 1, and you can't add 5p with 1 together. And so you wouldn't, like, this would be it. This is all you can do if you were to try to add that pq with 2p squared q. I hope that that's sufficient to demonstrate that you cannot, in fact, add those terms together. Like terms can be added with like, but if you've got different exponents on the variables, you may not, in fact, add them together. Now, when it comes to these expressions, these polynomial equations that we might be adding with one another.
Oh, I don't know what just happened there. I don't know what just happened. Suppose we are trying to, instead of add these expressions, we actually have a subtraction scenario happening. The reason why I state that a polynomial expression's degree
Acts much like the order of the individual digits of a specific number has to do with how one may algorithmically add or subtract two or more polynomials from one another. It turns out that, if we have 150 minus 75, you guys know that you can, of course, line up your 5 digit with your 0 digit because these are in the ones place. And of course, we may add or subtract our tens digits from one another because they are in the same place, if you will. For a polynomial expression, you may do a very similar thing. When you have like terms, such as this 2p squared q, you may, of course, say that because we are subtracting from this 2p squared q this term, which is its like term, 3p squared q, we could, of course, line these two terms up more or less column-wise when we're doing the subtraction. And of course, 2 minus 3 gives you a -1. And p squared minus p squared, of course, we would have a p squared left there and a q term left over as well. So you'd have a -1 square p, a -1 p squared q from this subtraction operation. Now, the thing to remember with subtraction is that we're not just subtracting that 3p squared q term. We're also subtracting the 9pq squared term. We would also be subtracting the -6pq term. And so instead of doing things in terms of an algorithm, like what we're doing here, what we need to remember is there is, in fact, underlying algebra rules that govern how you can, say, add these different terms together, or in this instance, how you can subtract these different terms from one another. And what we need to remember is the relationship between subtraction and the addition of negatives. So you'll remember that at the beginning of the semester, we discussed how whenever you take away a term from another term, it's the same thing as adding a negative. And when you add a negative number, that's the same thing as adding a -1 times a specific number. Here is where we are going to use this fact. We could say that this expression is the same as adding a negative 3p squared q plus 9pq squared minus 6pq. And that because we're adding this negative number or this negative polynomial expression, that would be the same thing as having -1 that is multiplied out in front of the entire polynomial expression itself. So you've got a -1 that's multiplied in front of this entire second expression. And for my first expression, that more or less just stays the same. I'm not going to do anything with that. So now we would have to distribute the negative throughout this entire second set of parentheses. And while a lot of students are going to start skipping steps here, I would highly recommend that when you're just starting out, go ahead and write everything out long form just so you don't make a mistake. Mistakes are very easy to make. So you're going to have 2p squared q plus 5pq squared plus pq plus -1 times 3p squared q plus a -1 times 9p q squared plus a negative 1 times a negative 6 pq. Negative negative is a positive. 6 times 1 is 6. So we have a 6 pq. Positive negative is a negative. 1 times 9 is 9. So you have a 9 pq square here. Positive negative is a negative. 3 times 1 is 3. P square q is left over. And you've just got 2p squared q plus 5pq squared plus pq. And at this point, you can kind of use your commutative law to group up your like terms. So I've got my p squared q's with p squared q's, my 5pq squareds with the negative 9pq squared terms, and then, of course, my pq with my 6pq. So at the end of the day, we've got a negative 1 p squared q minus 4 pq squared plus 7 pq. And that's my answer. It's pretty straightforward. Well, I would say the only trick is really remembering that you have to distribute the negative 1. Now, for a lot of students, this is going to seem like a lot of work, but you have to build the endurance in order to be able to succeed in college algebra. We need to build endurance here for these lower level problem statements. And then what you're going to see is that the endurance that we build at this point in time is going to serve us tenfold over as we go into Math 1100, and you'll see the level of difficulty jump at Math 1100. And then once we get to college algebra, the level of difficulty will kind of plateau. It will be as difficult as things will get, more or less. And then when you get to pre-calculus and or calculus 1, in my opinion, calculus was actually easier than college algebra. That's just my opinion. You know, everybody has their own opinion, but I would say that calculus was actually easier than college algebra in the sense that you either understood what was going on in college algebra or you didn't. Okay. But if you understood what was going on in college algebra and you really applied yourself, then once you got to calculus, then all what you saw was all calculus happens to be is simply an extension of the rules that you use inside your algebra class. And so because that's the case, and you've already presumably mastered those lower level skills in your algebra courses, you're gonna find that calculus is actually rather straightforward. Okay, so 5.2, section 5.2 deals with multiplying polynomial expressions. It turns out that while we may, of course, add and subtract polynomial expressions from one another, you may, in fact, also multiply two or more polynomial expressions with each other. So I may take a 7x plus 1, and I can multiply this with a 2x plus 3. And if we do this, we're going to be able to create a new product, which is going to look rather interesting. But the question, of course, is how do we go about doing this? Now, naturally, if we knew what the x was, you can imagine, like, say we knew x was 1. So you would just plug in a 1 everywhere you saw an x term. So you'd have 7 times 1 is 7 plus 1, and 2 times 1 is 2. So you'd have 2 plus 3. So 7 plus 1 is 8. 2 plus 3 is 5. So then 8 times 5, of course, gives you 40. And so everything would be A-okay. But in this instance, we actually don't know what our x term happens to be, right? And then in that case, well, what do we do then? What are we going to do then? While we do not know what our x term happens to be, if we did analyze the situation of 8 times 5 yielding 40, we can in fact get a clue as to how we can multiply these two binomials together with one another. Consider, for example, that I hope everyone would agree 5 is the same thing as 3 plus 2. Okay, 8 is the same thing as, say, 4 plus 4. So the question is, how can I multiply 3 plus 2 in such a way with 4 plus 4 that I generate or I yield the number 40, which is what we both agree, or what everybody should agree, is the result of 8 times 5. So the answer is, if you had taken this first term and you had multiplied it with 4 plus 4, and we had taken this second term and we multiplied it with 4 plus 4, this would indeed give you the answer of 40, because 3 times 4 plus 4, or 3 times 8, plus 2 times 8 would give you, well, 3 times 8, 8, 16, 24. And 2 times 8 is 16. 6 and 4 is 10. So you'd have 2 plus 2, or 40. All right. So that would indeed give you your answer. Now, as it turns out, if we backed up to this second operation here, where you have the 3 times 4 plus 4 and the 2 times 4 plus 4, another way we might have worked through this problem would be to use the distribution law at this point in time. So you'd have 3 times 4 plus 3 times 4 plus 2 times 4 plus 2 times 4, and realize that the distribution law is going to work out, because at the end of the day, whether we had added these terms inside of the parentheses first, or whether you had distributed and then add, that's going to be exactly the same thing. So 3 times 4 is 12. 3 times 4 is 12. 2 times 4 is 8. 2 times 4 is 8. 8 plus 8 gives you 16. 12 plus 12 gives you 24. And voila, you're exactly where you were over here. This process of taking your first term, added with the second term, and multiplying it with the first term of the second set of parentheses added with the second term of the second set of parentheses, this is called extended distribution. We may have discussed extended distribution in one of our earlier lectures, but more formally, what you do with extended distribution is you're going to take your first number of the first set of parentheses and you will multiply it with everything in your second set of parentheses. You then add this with the second term of your first set of parentheses that will be multiplied with the everything of the second set of parentheses, so your C plus your D term. Now, at this point, you can use distribution, so you're going to have A times C, and we'll have A times D, we'll have a B times C, we'll have a B times D. So this will be our theoretical result or theoretical equivalence between if we actually knew what our A and B were, and we added those together, and we then multiplied that result with the addition of C plus D. We should find that there's, in fact, an equivalence between these two expressions. Now, what we're going to do here is, if you guys can kind of see, we have the same setup. Here's my A, here's my B, here's my C, here's my D. So what will happen, according to our extended distribution law, is you're going to have A times the C plus D term. In this instance, it'll be the 7x times 2x plus 3, and we'll have that added with the b, or 1, multiplied with the c plus d term. And so now we're going to do distribution law. We'll have 7x times 2x plus 7x times 3 plus 1 times 2x plus 1 times 3. 7 times 2 times x plus 7 times 3 times x plus 1 times 2 is 2. X plus 1 times 3 is 3. Note that for this 7x times 2x, the associative law at this point in time kicks in. So you may remove the set of parentheses. And if you did that, you'd have 7 times x times 2 times x. Then by that point, the commutative law kicks in. Because remember, you can't utilize the commutative law before you remove the set of parentheses. So it's only after you remove the set of parentheses and you have everything multiplied with each other that you can then use the commutative law and group your numbers with numbers, x's with x's. But that's kind of what I'm doing in my head right at this moment. And then when we have the 7x times 3, I'm doing the same thing. You're going to have 7 times x times 3 according to the associative law. And then by the commutative law, you may do some regrouping. So you'd regroup your 7 with your 3, and you'd have your x left over. Now, right here for this 1 times 2x, you've just got to multiply your numbers with numbers. And the same is true for this last term, 1 times 3. We can go ahead and multiply our numbers with numbers. It's not really too complicated mechanically. So 7 times 2 gives us 14. X times x is x squared. 7 times 3 is 21. And we've got a 2x and a 3. 21 plus 2x, that gives us 23x. We have a 3 left over and a 14x squared. All right, so we've got 14x squared plus 23x plus 3, and that's all we've got to do. Good job, guys. Good job. Let's look at another one that's a little bit more complicated. Let's say we've got 5x cubed plus 3x squared plus 5x plus 1. And this is multiplied with 2x squared plus 3x plus 4. All right. While extended distribution is generally nice when you have two terms, you can actually break up a term into many different addition and or subtraction operations. And so instead of, say, 3 plus 2 giving you 5, I hope everyone would agree that's the same thing as 1 plus 1 plus 1 plus 1 plus 1. That is also giving you 5. So you could have done 1 plus 1 plus 1 plus 1 plus 1, all multiplied with, say, 4 plus 4. And if you had done this operation, you would still obtain the number 40 by simply doing a bunch of 1 times 4 plus 4 plus 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 1 times 4 plus 4. So you could have done it that way. I wouldn't have done it that way, but it's theoretically possible. And if you do it, then you'd see that your distribution laws hold for that instance as well. And so the long and the short of it, because you can do it that way, anytime you have like more than two terms in a second set of parentheses multiplied by, say, another polynomial with more than two terms, you're just going to create a very long distribution problem. You're going to, in this instance, do 5x squared times 2x squared. I'm sorry, 5x cubed, rather, times 2x squared plus 3x plus 4. We have to take the first term and we're multiplying it by everything in that second set of parentheses. So I've got 5x cubed, since that's my first term, and I've got to multiply with that entire second set of parentheses, okay? And then what I'm going to do is I'm going to add it with, in this case, 3x squared, which would be similarly multiplying through everything in the second set of parentheses. I'm going to add it with 5x, which will be multiplied with everything in the second set of parentheses. And I add it with 1 times these terms all multiplied through that second set of parentheses. So now what we've got to do is we've got to do a long distribution problem. You're going to have 5x cubed times 2x squared. We'll do 5x cubed times 3x. We'll do 5x cubed times 4. And of course, this will be added with 3x squared, which itself is multiplied through all of these different terms. And of course, this will be added with 5x, which will be distributed through the entire second set of parentheses.
And note, guys, this is where a lot of students get burned out because it is a lot of writing. We're just going to have to develop our stamina for mathematics, okay? Like it's just that straightforward. We have to develop
Stamina.
All right. And so you've got 5x cubed times 2x squared plus 5x cubed times 3x
Plus 5x cubed times 4. That added with 3x squared times 2x squared, 3x squared times 3x, 3x squared times 4. That added with 5x times blah, blah, blah. That added with 1 times blah, blah, blah. And so basically, you're just going to do this one unit at a time. You got to start at the beginning, 5x cubed plus, I'm sorry, 5x cubed multiplied with 2x squared. You can, of course, remove all of the parentheses.
And if we just look at our 5x squared terms, then what you've got is you've got 5 times 2, which is 10. You're going to have an x cubed and an x squared. If you've got 5x cubed times 3x, you've got really 5 times 3, x cubed times x. If you've got a 5x cubed times 4, we've got 5 times 4x cubed. Now, here's the interesting thing. This kind of leads into our chapter 5.2. What happens with our exponents is rather interesting. You could have the x cubed is the same thing as x times x times x, and the x squared is the same thing as x times x. So all in all, this is going to be
X to the fifth. And what you'll see is it's almost like your exponents add with one another. In this instance, you have 5 times 3 or 15. X cubed is x times x times x times x, which will be just another x. So you've got 10x to the fifth plus 15x to the fourth, almost as if the x was raised to the first power and 3 plus 1 gave you 4. The 10x cubed times x squared, it was almost like the 3 added with the 2, giving you the exponent 5. And with 5 times 4, that gives you 20. X cubed is just x cubed. Of course, we're not done. That was just our top row. We now would have to address this second row, which is the 3x squared times 2x squared. So you've got 3x squared times 2x squared plus 3x squared times 3x plus 3x squared times 4. And of course, that is going to be 3 times 2 times x squared plus 3 times 3 times x squared times x plus 3 times 4 times x squared. 3 times 2 is 6. X squared is the same thing as x times x. So you've got x times x times x times x. 3 times 3 would be 9.
So you've got 9, and then just an x times x left over, and 3 times 4 is 12, x times x. Okay. I've got 4 x's all multiplied together, so I've got an x to the fourth, 9 followed by 3 x's, so an x to the third, and
12 followed by x times x or x squared. Of course, if you look carefully here, it's almost like the exponents are adding 2 plus 2 to give you that 4. And here, if you, of course, instead of writing x just by itself, you wrote x to the first power, you would see that you have 2 plus 1 gives you 3, which of course is the exponent on the second term. So there is indeed a pattern, which we will learn about here in the next section. And of course, we're not finished. We still have to do this third row. So you've got 5x times 2x, what is it, squared plus 5x times 3x plus 5x times 4. You've got 5 times x times 2 times x plus 5 times x times 3 times x plus 5 times x times 4. By the associative law, by the commutative law, you may group your terms together. So 5 times 2 times x times x times x, and 5 times 3 times x plus 5 times 4 times x. And we have 5 times 2 is 10. X times x is x cubed. 5 times 3 is 15. X times x is x squared. 5 times 4 is 20. And just x is left by itself. And of course, 1 times anything is just that something. So for our final row, we've got 2x cubed plus 3x plus 5x. So if we add everything together now, remembering that we're going to take the last row of our equation. So we're going to add everything together. We've got 10x to the fifth plus 15x to the fourth plus 20x cubed. 15x to the fifth, sorry, 10x to the fifth rather. 10x to the fifth plus 15x to the fourth plus 20x to the third. We'd be adding that with 6x to the fourth plus 9x cubed plus 12x squared. We're going to be adding that with 10x to the third plus 15x squared plus 20x, which would be added with 2x cubed plus 3x plus 5.
Sorry, plus 4 instead of this should have been a 4. So this should have been a 4. Okay. Now, using the commutative law, you're going to group
your x to the fourths together. So you'd have 15x to the fourth plus 6x to the fourth. You would group your 20x cubes together with your 9x cubed, with your 10x cubed, and your 2x cubed. Okay. And then we would group our 12x squared together with our 15x squared, and our 20x with our 3x, and our 4 would be what is left over. So in total, 10x to the fifth, nothing happens there. 14x to the fourth is being added with 6x to the fourth. So now you just have, well, 15 plus 6 gives you 21. So we should have 21x to the fourth. 20 plus 9 is 29. 29 plus 10 gives you 39. So you'll have 39x to the third plus 2, rather 2x to the third, which should give us 41, rather. So we should have 41x to the third. Of course, that will be added with 12x squared plus 15x squared, which 10 and 10 is 20, 5 and 2 is 17. So you've got 27x squared, 20 and 3x, I'm sorry, 20x plus 3x is 23x, and you have a 4 left over. So your answer, after everything is said and done, is 10x to the fifth plus 21x to the fourth plus 41x to the third plus 27x squared plus 23x plus 4. You can do all of this math. You guys can do it. It is very long, but it is possible as long as you work it one step at a time. Yes, it does take 20 minutes per problem. So it will take you a lot of time to actually be able to master the concepts in this section. But what I would tell students is all you are doing at a fundamental level, after you get past the abstraction of like, you can expand a term, you can use the associative law, you can use the commutative law. As soon as you guys really master this idea that we can apply the rules of algebra in these situations that you see right here, and you get a hold on, say, mastering the commutative law and externalizing when you use the commutative law, okay, what we're doing here is just multiplication, really. What we did from this step to this step was just apply a definition of exponentiation, which we should have learned in our Math 900 courses or in our high school program at some point in time. And then, of course, when we're adding like terms together, again, that's just an extension of the commutative law and or just our general common sense about adding bananas with bananas and apples with apples. And so at the end of the day, all this really happens to amount to is just either remembering definitions of exponents, being able to multiply things correctly, and or being able to add bananas with bananas and apples with apples. That is really all we're doing here, beyond all of the fancy equations and or algebraic nonsense. Okay. However, as we are multiplying these polynomial expressions with one another, what you're going to see is this idea that basically, there are certain patterns that emerge when you multiply your monomial terms with monomial terms. So when you were multiplying, say, 4x squared with, maybe a 2x term, okay, if you were to do this, this, of course, is a monomial. And this term here is also a monomial. And it turns out that when you are multiplying monomials with monomials, the laws of exponentiation kick into play. So that is what we are going to now look at together.
Okay, recall from your high school courses, your lower level high school courses,
Or your math 900, that whenever you take a number and raise it to a power, and then you multiply it with a number raised to the same power, that you add the exponents. This is called the exponent addition law. The reason for this is if you have, say, 2 to the third times 2 to the fourth, what's going to happen is you could expand this first term, the 2 to the third, as 2 times 2 times 2. Here's my 2 to the third. And if I expand my 2 to the fourth, I have 2 times 2 times 2 times 2. And then, of course, if I remove my parentheses, according to the associative law, then you just have this string of 2's that are all multiplied by each other. And according to the definition of an exponent, the definition of an exponent says that whenever we have a number that is multiplied by itself a certain number of times, that is just the same thing as taking the number and raising it to a specific power. So in this instance, we have 2 multiplied by itself 7 times. So we may write this as 2 raised to the power of 7. That's just the definition of exponentiation. We discussed this at the beginning of the semester. So I'm going to assume that everybody understands what we're doing at this point in time. Now, instead of raising this 2 to the third power, I could have raised it to the 2 to the fourth power. And if I multiplied 2 to the fourth with 2 to the fourth, you'll see that nothing much really changes. Instead of having 3 sets of 2's multiplied together, multiplied with the 4 sets of 2's, now I've got a 4 sets of 2's. And once I remove my parentheses in accordance with the associative law, I've got basically 8 2's all multiplied together. And so if we, consider what's happening with these exponents, I hope everybody would agree that 4 plus 4 gives you 8, and 3 plus 4 gives you 7. And so all that is really going on is the exponents may be assumed to have an additive relationship with one another just because of the rules of the commutative and or the associative law under multiplication. And it really doesn't matter how many sets of something that you might be multiplying together. You might have, say, instead of 2 to the fourth, you could have said 2 squared times 2 squared, because the exponents here would, of course, add together. 2 plus 2 gives you 4. And we could have said, instead of 2 to the fourth, we also had another set of 2 squared times 2 squared. But regardless, because the base of these numbers is the same, whenever we go to actually calculate what all these quantities must be equal to, all you have to do is look at the exponent and say, all right, well, this number 2 must be raised to 2 plus 2 plus 2 plus 2, or 2 plus 2 is 4, plus 2 gives you 6, plus 2 gives you 8. So we would have 2 raised to the 8th power. And you can, of course, determine that that must be the case by simply expanding your expression. And then under the associative law, you have a bunch of 2's all multiplied together. And once you count them up, you get to the 8th. So it doesn't matter exactly how many terms you multiply together. You are just going to look at the exponent of the term, whatever term it happens to be, and you will simply add those exponents with one another. Another example. Suppose I have m to the 15th times m to the 10th times n to the 30th times n to the 45th. I wanted to calculate what this happens to be equal to. Well, according to the addition law of exponents, I may take my m to the 15th and m to the 10th, and because these have the same base, I may raise m to 15 plus 10. And I also may look at the n to the 30th times n to the 45th, and because they're the same base, I may add the exponents, 30 and 40 together. 15 plus 10 is, of course, 25. 30 plus 40 gives me 70. So my answer is m to the 25th, n to the 70th. Now, it would be very difficult for a student to actually, expand out this expression. You'd have to sit here writing n, 30 times. And then here you'd have to write another n 45 times. And I hope that you can see that because you have 30 sets of n multiplied with 45 sets of n, in total, that would be the same thing as 70. I'm sorry, not 70. It should be 80 sets of n. Well, so they're actually 45. 40 plus 30 gives you 70. 5 plus 0 gives you 5. So 75 sets of n. So 75 sets of n total. Okay, just to make an argument. Now, these are often used for standardized tests. You might have a standardized test which asks you m to the 105 times n to the 273. And what is this equal to? And naturally, students who don't remember or don't know their exponent laws are going to freak out whenever they encounter this question on a standardized test. But if we remember our exponent laws, then all we have to do is add the exponents together with one another. So you'd add the 273 with 273. I'm sorry, you're going to add the 273 with the 105. And what that gives you is 5 plus 3 is 8, 7 plus 0 is 7, 2 plus 1 is 3. So you have m raised to the 378. And that would be your answer. It's that simple. Interestingly, there is an extension to the exponent addition rule, which is called the exponent product rule. So exponent product rule. What your book refers to as the exponent power law. Okay. And that is whenever you have a situation where you take a number and you raise it to a power and then you go ahead and exponentiate that, it turns out that it's the same thing as taking your number raised to the product of the two exponents. So for example, if you have 2 to the third and you raise it to the fourth power, all you have to do according to the exponent product rule is you take the base number, which is 2, you raise it to the power of 3 times 4, which gives you 12. Now, the reason for this happens to be related to what's actually going on with the exponent addition law. Consider, for example, if you have 2 raised to the 8th. So 2 raised to the 8th, we could say, was the same thing as 2 to the 4th times 2 to the 4th. But note at this point that you have 2 sets of 2 raised to the 4th power. So this, technically speaking, would be the same thing as saying that you have 2 to the 4th quantity squared. Okay. Consider also that 2 to the eighth, technically speaking, would be the same thing as 2 squared times 2 squared times 2 squared times 2 squared. 2 plus 2 gives you 4, plus 2 gives you 8, plus 2 gives you, sorry, 2 gives you 6, plus 2 gives you 8. So since you have all of these 2's raised to a power, they're all the same base, you may add across the exponents, and you will indeed get 2 to the eighth power. But since I have each of these terms raised to the same power, I could also say, look, this is the same thing as 2 squared raised to the fourth power in this instance. Okay? And of course, 2 to the eighth would also be the same thing as 2 times 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the first raised to the eighth. I hope I've made a sufficient case that the product rule is something that is legitimate under the ordinary reasoning of just the definitions of exponentiation. And so, if you have a situation such as -4 raised to the 10th power, and then you take that and you raise it to another power like 20, and somebody asks you, what is this going to be equal to? Just using the definitions that are available to us and understanding that the exponent product law says that we need to multiply these numbers together, we're going to take our -4, we're going to raise it to the power of 10 times 20, which of course gives us 200. So you'd have -4 raised to the 200th power. Okay. Finally, we have what is known as the exponent distribution law. Exponent distribution law really has two different forms. If you take, say you've got two or more numbers all multiplied together, and maybe they are raised to a specific power, you may say that each one of these terms is raised to the specific power. On the other hand, if you have a number raised to, say, some power multiplied with another number raised to a different power, and that is raised to a power, then you may say that each one of these individual terms will be raised to whatever the power is on the outermost set of parentheses. So you've got an a raised to the k raised to the m times b to the j to the m, and your exponents will then multiply with one another. So you've got a to the km times b to the jm. Okay, an example of this would be if you have 3s to the fourth and you raised it to, say, the fifth power. By the exponent distribution law, you're going to take each of your numbers inside of your parentheses and you raise it individually to a specific power. So you take 3, raise it to the fifth power. So 3 to the fifth, of course, is 3 times 3 times 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3. 3 times 7, 7, 14, 21. 3 times 2 is 6, plus 2 gives you 8. So you have 81. And 81 times 3 is going to be 3 times 1 is 3. 3 times 8, 8, 16, 24. So you have 243 s raised to the 4 times 5, which gives you s to the 20th. Okay, if you have 4a to the fifth, b to the seventh raised to the fifth power, or we'll say it's raised to the third power. This is going to be the same thing as 4 to the third times a to the fifth to the third times b to the 7th to the 3rd. 4 to the 3rd, 4 times 4 is 16. 16 times 4 should be 64. You'll have a to the 5th times 3, b to the 7 times 3 by the exponent product rule. 5 times 3 is 15. 7 times 3 is 21. And you have a 64 left over. Of course, go ahead and check that. 16 times 4. 4 times 6 is, of course, 24. Carry your 2. 4 times 1 is 4 plus 2 does indeed give you that 64 that you need. Things in this particular chapter are not too bad outside of what we have discussed here in this section. Things really only get tricky when you start to add in a bunch of fractions and whatnot. So, but let's look at problem 93. This would be page 323. So problem 93 says that you've got -3 times -5 cubed squared, and you've got 2/5 m to the 5th n all raised to the 3rd power. It asks you, what is this equal to? So first of all, guys, by PEMDAS, we cannot just ignore that you've got these terms that are multiplied by each other raised to some power, raised to some exponent. And then by PEMDAS, if you actually look inside of your parentheses, there's not a whole lot that you can do with 2 to the 5th, 2/5 m to the 5th times n, or -5 m n cubed. This would be a good indication that you have a problem where the only solution lies in some of the other properties of algebra. In this instance, the properties of the exponent laws. And the exponent law that we're going to need is, of course, the exponent distribution rule, as well as the exponent product rule. So first of all, we're going to distribute this 2 to each of these terms. You're going to have -5 to the 2nd, m to the 2nd, n to the 3rd raised to the 2nd. And don't forget your -3. And then for the second set of parentheses, you'll have 2/5 to the 3rd power, m to the 5th to the 3rd power, n to the 3rd power. -5 times -5 is 25. So you have -3 times 25. M squared is just m squared. And n to the 3rd raised to the 2nd power is going to be n to the 3 times 2. 2/5 to the 3rd power. Remember, guys, this is just 2/5 times 2/5 times 2/5. 2 times 2 is 4 times 2 is 8. So you have 8 over 5 times 5 is 25 times 5 gives you 125. So you've got 8 over 125 here. And you've got m to the 5 times 3 and an n to the 3rd power. Okay. So -3 times 25 is -75. I'm going to go ahead and pull my 8 over 125 forward just so that I can organize my numbers. And those who want to simplify this fraction can attempt to do so. But what I'm going to do instead is I'm going to look at trying to group my m's and my n's together. Note that m to the 5 times 3 is m to the 15th. N to the 3 times 2 is n to the 6th. So I've got some m and n terms that can also be simplified. Now, looking at 75 and 25, note that 25 can go into 75 3 times. 25 can go into 125 5 times. So this is the same thing as -3/5, all multiplied by 8. M to the 2nd times m to the 15 is going to be m to the 2 plus 15. And n to the 6 times n to the 3rd is going to be n to the 6 plus 3. Negative and positive is negative. 8 times 3, 8, 16, 24. So you'll have -24 over 5, m to the 17th, n to the 9. And once you guys get good at being able to work through these problems, you're going to be able to do it probably faster than I am, okay? Like I have to really, work through things one step at a time. I don't feel super comfortable about just my mental math, especially with these problems where I tend to make a lot of like really petty errors. So for me, I really force myself to do everything one step at a time, and I externalize that information. But for a lot of students, once you've developed your mental math, you can really do these problems rather quickly. They could just blow through the problems in chapter 5 as if they were nothing. So, but for now, we've discussed chapters of 5.2, 5.3, and 5.1. And so I feel that we have really talked about everything that we need to talk about this particular week. And so at that, I'm going to let everyone go.